Hello, my name is David Shriver, and today I'm going to be presenting our paper on reducing DNN properties to enable falsification with adversarial attacks. Deep neural networks are increasingly being applied in safety-critical domains. The DroneNet network is a model trained on driving data to autonomously pilot a UAV, inferring a steering angle and probability of collision from a given black and white image. To assure the safety of such systems, it's essential that we are able to check that they conform to a given safety specification. One commonly checked property is adversarial robustness, which checks whether small perturbations to a known input can significantly change the output. In the case shown here, a small, imperceptible change to the original image completely changes the predictions of the network. However, there are many other types of safety properties that we may wish to check. For example, for the DroneNet model, which was trained on data recorded while driving down a highway, we may wish to specify that for all inputs, like the one shown here, if the predicted probability of collision is low, then the model should not predict sharp steering angles. Here we specify that for all inputs that are predicted to have a probability of collision less than 0.1, the DroneNet model should not output a steering angle greater than 5 degrees in either direction. While DNN verification has advanced considerably in recent years, verifiers still struggle to scale to large or complex models, such as DroneNet. Complementary to verifiers, falsification methods, such as adversarial attacks, are a powerful tool for finding violations to local robustness properties of DNNs. While these attacks are often fast and scale well to large networks with complex structures, there are many other types of properties, such as the DroneNet property mentioned earlier, to which adversarial attacks cannot be directly applied off the shelf. In this work, we'll focus here on increasing the property support for falsifiers. We identified the key insight that many properties can be reduced into properties of other forms, such as local robustness. Building on this insight, we develop an approach for reducing properties in an expressive general form to an equivalid set of properties with some specified form. In particular, in this work, we reduce to robustness properties in order to enable the application of adversarial attack methods. This reduction enables the application of adversarial attacks to quickly find property violations for a broad range of properties. Our reduction takes in a DNN and a property, which we refer to as a correctness problem, and produces a set of correctness problems, each with a modified version of the original DNN and a robustness property. The reduction has two key properties. First, the set of robustness problems produced by the reduction is equivalid with the original correctness problem. If a violation exists for the original problem, then a violation will exist for at least one of the new subproblems. And if no violation exists, then none of the subproblems will have a violation. Second, each subproblem uses the exact same property type. In particular, for this work, we reduce to robustness properties that specify that all inputs from the unit hypercube are classified as a single class, class 0. This allows falsifiers and verifiers to support a large set of correctness problems by implementing support for this single property type. While this reduction does turn a single problem into multiple problems, the subproblems are all independent and can be checked in parallel. To enable the same property to be used for all subproblems, we construct DNNs for the subproblems using two key transformations to the original network. First, we incorporate a prefix network that maps values from the unit hypercube to the input region of the DNN to be verified. And second, we append a suffix network that takes in the inputs and outputs of the original DNN model and classifies whether they constitute a violation of some fragment of the original property. In the next few slides, we will describe this reduction in more detail in the context of the DroneNet property introduced earlier. Our reduction first reformats the property to facilitate splitting the property into subproblems. We negate the original property specification and convert it to disjunctive normal form. In this form, any model that satisfies a disjunct violates the original property. The reduction will define a new correctness problem for each of these disjuncts. In the case of this property, we end up with two disjuncts as shown. For each disjunct, we convert the constraints to a half-space polytope defined over the inputs and outputs of the original DNN. A half-space polytope can be represented with the matrix inequality AX less than or equal to B, where A is a matrix of k rows, one for each constraint, and D columns, one for each variable. In this case, each variable is an input or output to the original DNN. This form will facilitate the construction of the prefix and suffix networks in the next steps. For the prefix, we can use the constructed half-space polytope to build a prefix to the original network that maps points from the unit hypercube to points within a hyperrectangle that bounds the input constraints of the disjunct. This is done by extracting lower and upper bounds for each input variable and using them to define a mapping from the range 0 to 1 to the range defined by the computed bounds. This step serves a couple of purposes. First, it ensures that every subproblem uses a network with the same input domain, which simplifies property specification. And second, it enables some simplification to the suffix in the next step by allowing simple input interval constraints to be discarded, since they are already encoded in the prefix. In cases where all constraints over inputs are simple intervals, as is the case with this DRONet property, this allows the suffix to be defined only over output variables. We next construct a suffix to the original model that classifies whether inputs and outputs satisfy the corresponding disjunct. This suffix has two classes. Class 1 indicates that an input and output satisfy the disjunct, and class 0 indicates that they do not. The suffix is made up of two layers and is built using the half-space polytope. The hidden layer uses A as the weight matrix and minus B as the bias vector. It will have a neuron for each constraint, each of which will be less than or equal to 0 if the constraint is satisfied. If we apply a ReLU activation, then a value of 0 indicates that the constraint was satisfied, and any positive value indicates that it was not satisfied. If we then sum these neurons to get the output for class 0, a positive value indicates that the disjunct was not satisfied. We can then specify that the output value for class 1 is always 0. If this value is ever greater than or equal to the output value of class 0, then the disjunct is satisfied, and thus a counterexample exists for the original property. It is this suffix that turns the network into a classifier that enables us to specify a robustness property over the new network. Finally, we can construct the subproblem corresponding to this disjunct. We build a modified network by incorporating the prefix and suffix, and then construct the correctness problem with a robustness property stating that inputs from the unit hypercube map to class 0. We can then repeat this process for each disjunct, resulting in two subproblems for this particular property. And again, these problems can be checked in parallel. We've implemented our reduction in a tool which we call DNNF. Our tool accepts DNN models in the ONNX format and properties written using the DNNP property specification language. DNNF applies property reduction and then runs one of several available backend falsification methods and reports a result. To evaluate the expressiveness of the property specifications supported by our reduction, we analyzed 17 existing verification benchmarks along with 2 novel benchmarks. We categorized the properties in each benchmark and analyzed whether they are supported by reduction. While off-the-shelf falsifiers only support one of the 8 property categorizations identified in these benchmarks, reduction enables adversarial attacks to be applied to 7 of the 8 property types that we've identified. We also evaluated our reduction using several popular adversarial attacks, as well as a fuzzing tool, comparing the effectiveness and efficiency to several verifiers. We demonstrate how our approach enables the application of falsifiers to the DRONet verification benchmark, which contains properties similar to the one we described earlier, as well as the Safari EQ benchmark, which consists of properties that assert equivalence between pairs of DNNs trained on the CIFAR 10 dataset. On a benchmark of 10 properties for the DRONet network, similar to the one described earlier, 2 falsifiers were able to find violations for all 10 properties, while the verifiers did not support the DRONet model at all. Similarly, while none of the verifiers could support the properties over multiple networks for Safari EQ, our reduction enabled falsifiers to be applied in order to find violations for as many as 112 of the 291 properties. Additionally, we evaluate the scalability of the reduction by checking 50 properties on 2 versions of a self-driving car model based on the Dave network. While the falsifiers sometimes find fewer violations on the larger model, the time to find violations does not significantly increase, with a median time to find a violation increasing by only half a second. In this work, we present an approach for reducing DNN correctness problems to facilitate the application of falsifiers, in particular adversarial attacks, for finding DNN property violations. We apply our approach to a range of correctness problem benchmarks and find that it enables falsifiers to quickly find property violations for many new property types. This allows checking properties of larger and more complex networks than with verification alone. Our DNNF tool is publicly available for download and reuse at the link shown. Thank you.